This is part 3 of the CMF's cone fundamentals and cone isolating stimuli tutorial. We've gotten down to here in parts 1 and 2, and now we're going to talk about cone sensitivity vectors expressed in the RGB tristimulus space. The idea here is we want to find a row vector such that when we dot product it from the left into the column vector representing the tristimulus coordinates, we compute the cone excitations for one of the cone classes. And if we had such cone sensitivities for each of the 3 cone classes, we could put them in the rows of a 3x3 matrix and use that to compute the LMS responses from the tristimulus values in the cone space. So if we think about the cone space, one thing we realize is that in the cone space, such sensitivity vectors are trivial to compute, namely they are the identity vectors 1, 0, 0 for the L cones, which picks out the first component of the LMS cone excitations, and so forth for the M and S cones. All right, so how do we derive these cone sensitivity vectors? What we can realize is that if we want to have be true, is that the cone excitations are independent of the space in which we compute them. So if we consider the L cones, what we're seeking is a row vector R such that we dot it into the column vector with the tristimulus coordinates of a stimulus, we get the L cone excitation. That's going to be obtained also by the vector 1, 0, 0, the first unit vector in the cone space, dotted into the cone excitation coordinates. So R is what we're after. T is the tristimulus column vector representing the stimulus, and U is a unit row vector, in this case 1, 0, 0, since we're talking about the L cones. And C is the cone excitation column vector. We also know that the tristimulus values are a matrix M times the cone coordinates, because we derived that above, M being the matrix M cones to CMF. If that's not clear to you, go back and watch the first 2 parts of this tutorial, or scroll upwards in the tutorial code where we went over that idea. In any case, since this equation here and this equation here hold for any choice of C, we have, and we set M here to be this matrix, we have R times M, plugging in for T, is equal to U, since we just dropped off the C, since this equation has to be true for any C. And then that we can solve for by multiplying from the right by M inverse. So we have R, that's the thing we're after, is the unit vector times the inverse of M, which in this case is the matrix CMF to cones, which we also derived above. Notice that R, when we're done, doesn't necessarily have unit length. It's only in the cone excitation space where the response sensitivity vectors are guaranteed to be the unit vectors and to have unit length. Okay, so we can do that calculation, 1, 0, 0 dotted into M CMF to cones. In fact, we can do the same thing for the M cone sensitivity vector in the cone space and the S cone sensitivity vector in the cone space, which I've just stacked up here as 3 rows of the matrix. And so this code here gives us these response sensitivity vectors expressed in the cone space. And just as a check, I'll generate a bunch of random spectra as linear combinations of the color matching primaries, compute the cone responses directly from the spectra and the cone fundamentals, and also using this cone response RGB vectors applied to the tristimulus values. So we generate a bunch of random numbers, random tristimulus values between 0 and 1, 100 of them. We compute 100 spectra by multiplying the basis, the primary spectra in a matrix times those tristimulus values. And again, if that's confusing, go back and rewatch parts 1 and 2 of this tutorial series. That's discussed above, that general idea. Now we can get the cone excitations directly by taking the cone fundamentals and using them with the spectra, or we can get them from the tristim values by using this matrix here and multiplying it just times the random tristimulus values. We have a little tolerance, again, because these basis functions won't be exactly right, and we can check, but basically we'll discover that everything works within the tolerance. So no error was thrown. That's looking good. Let's just talk a little more about the idea above and expressing the thing a little bit differently, or maybe just saying it again because it takes a little while to absorb these ideas. Let's suppose we have a vector of cone excitations with values LMS, and we put them in a column vector. That's a point in the cone space. And in the cone space, as I said above, the sensitivity vectors are trivial and are the unit vectors. And so we can compute, for example, the L cone sensitivity as 100 times the LMS coordinates. And that's just what I was saying up here. U times C for the one choice of unit vector gives me the corresponding cone coordinate. In addition, the cone isolating vectors of unit length are trivial to write down in the cone space because they are the unit vectors where the cone excitation is 1 for the L cone and 0 for the M&S. Now in column vectors, that's a sort of trivial way in the cone space. It's very easy to say what the cone isolating direction is. It's the direction with a positive or a value only in the first coordinate. And similarly for the M and the S. So adding each of these vectors to any stimulus in cone space only affects the responses of one class of cones. So we can stack the identity cone sensitivity vectors in the cone space into the rows of a matrix, as in this code here, which we saw above, and that's just the identity matrix. And we can stack the cone isolating directions into the columns of a matrix. And again, we get the identity matrix. Kind of boring, two identity matrices. We interpret one case the rows and the other case the columns. Multiplying the cone sensitivity matrix into the cone isolating directions matrix gives us the identity back. That is to say, gives us the correct cone responses for the cone isolating directions, each in the column of a matrix. So this seems like a lot of multiplying the identity matrix into another identity matrix to get the identity matrix. But now let's think through the same calculations in the RGB tristimulus space. We know how to transform stimuli from cone space to RGB tristimulus space from all the work we did above. And so the three cone isolating directions in RGB space are given by going from cones to CMF times this matrix where each column is a cone isolating direction in the cone space. This gives us cone isolating directions in the RGB tristimulus space. And we've also argued above that the sensitivity vectors in the cone space are here. And I got a little wrap in my comment that I had preferred not to have. And so this here, where we use CMF to cones, gives us this matrix of cone response sensitivity vectors in the RGB space. And it better be the case that if we compute cone excitations in the same way as we did here, identity times identity getting identity, now if we take these response sensitivities times these cone isolating directories, we better darn well get the identity back. Otherwise, our computation of cone responses depends on the space we're working in, and that just can't be because the lights don't change depending on how we write them down. So if I take this expression here and I put it here and I multiply it by this expression here, which I've put here, what comes back should be the identity matrix. Let's just make sure that's true. Yes, it is. And it makes a certain amount of sense because this matrix multiply in the middle is a matrix times its own inverse. So that in turn will be the identity. And in the end, although what we've done is multiplied the identity times itself 3 times here to get back the identity matrix. So yes, it works. And examining this really tells us that to transform stimuli from one space to another, if we have a matrix that goes in one direction for the stimuli, we multiply from the left by, in this case, M's cones to CMF to move from cone space to RGB tristimulus space. That if we want to transform the sensitivities, we take the inverse of this matrix and we multiply from the right into the sensitivities, which are in the rows of this matrix. So that just tells us how we can transform both stimuli and sensitivity vectors in a way that everything works out the way it should. Let's try to visualize this a little bit in 3D and just understand it a little better. So I'm going to set up a plot to begin with. Let's see, I've run everything above. I'm going to set up a plot here, which I'm going to use eventually to represent things in the tristimulus space in 3D. And I'm just going to plot a point at the origin, put a big black dot at the origin so that I know where 0, 0 is. And this is a 3D plot, which I can swing around here once I start having a third axis. Okay, now I'm going to normalize the length of the isolating directions in the sensitivity vectors. This means they won't compute quite right, but all I want to look at here is the directions and the relations between them. And so this little loop just divides each of the relevant vectors by its own vector length to give me something that has length 1. And I'm going to plot first in the tristimulus space the L-cone isolating direction. So I'm going to use plot 3 to do that. And if everything's worked right, I should now have a nice vector here in the 3 space. I guess I have to do something to the axes to make this rotate the way I'd like it to. So I can see all, there we go, start to see all 3 dimensions. I haven't put labels on yet. Let me, in fact, add the labels down here. So I want to go through this graph one step at a time. Can't open. Surely you can run it, though. And let's bring that back. Okay, so now I've got these labeled a little better. The R, G, and B tristimulus values, all with equal length. And there happens to be the direction. When I traverse in this direction, I'm isolating the L cones. Now, I did that. Let's add in now the M and the S cone sensitivity directions. And here they are. And what ought to be true, since the way I compute responses is that I dot the stimulus vector. I take the dot product of the response sensitivity vector and the stimulus vector. The L cone isolating direction is supposed to produce 0 response in the M and the S cones. And geometrically, that means it ought to be orthogonal to those 2 response vectors. If it's not orthogonal, when I take the dot product, I'll get something that isn't 0. And that means that something isn't right, because this stimulus vector is supposed to have no effect on the L and the M and the S cone mechanisms represented by their sensitivity vectors. And I can be a little fancy and just fill in a plane that spans those 2 vectors in the plot. Just make it a little easier to see what's going on. So now I have this plane that contains exactly the M and the S cone sensitivity vectors, and you can see visually here that the L cone isolating stimulus is orthogonal to this plane, and it stays. I can rotate it around. It's very nice, nice and orthogonal there. If you don't believe the visualization, you can also just compute the angle between them using the fact that the dot product of 2 vectors is the cosine of the angle between them. And take the arc cosine in degrees and print it out. We better get 90 degrees here twice, which we do. Okay, now let's add in the L cone sensitivity vector. If you think about it, there's no necessary relationship between the L cone isolating direction and the L cone sensitivity vector. They happen to be lined up in cone space along the L cone axis. But that's actually no longer true when we represent things in some other space. What has to be true is the L cone isolating vector has to project onto the L cone sensitivity vector. Otherwise, it wouldn't have any effect of the L cone. So it can't have a 90-degree angle between them, but it could have any other angle that isn't 90 degrees. And again, just to see that that is the case, we can now look here at this L cone sensitivity vector. It's not sitting in the plane with the M and the S, and you can see that it's got an angle relative to the L cone isolating direction that isn't 90 degrees. It's slightly less. And in fact, we'll just check that numerically here. It's 77 degrees in this case. So this is a kind of interesting plot to try to make sure you understand. We've got the 3 dimensions of the tristimulus space, and in this space, any stimulus is represented by a vector in the space. They happen to be centered around 0 here. I haven't worried about negative light or any of that. And in real experiments, you would add all these vectors to some stimulus that had positive power and talk about the differences between them. But the geometry wouldn't change, it would just shift the origin. And the key thing is that the L cone isolating direction is defined as orthogonal to the sensitivity vectors of the M and S cones. And that orthogonality has to remain true no matter how I transform color spaces, and it will as long as we transform the sensitivity and the isolating directions, the stimulus vectors, in the way I've described above. The L cone isolating direction doesn't have a necessary relationship to the L cone sensitivity vector, but what would be true is that, say, the M cone isolating stimulus vector would have to be orthogonal to both the S cone and the L cone sensitivity vectors. That's you can explore that on your own and check it out. I won't make a plot here of it, simply by changing which set of stuff we're plotting using the same basic idea, which will involve changing some of these indexes to where one in the columns is the L cone for stimuli, and 2 in the rows is the M cone for response vectors, 3 in the rows is the S cone for response vectors, etc. This code here is a little obscure to make this filled in plain, but if you look through it, you should be able to figure it out. So as a kind of exercise, you could verify that these basic geometric relationships that have to hold also hold for M cone isolating and S cone isolating stimuli with respect to the sensitivity vectors of the other two cone classes. So that's the end of the tutorial, because the only thing left is this code I ran before, which prettied up the axes. And with this, I think you should have a better understanding of tristimulus spaces, cone spaces, transforms between them, and how cone isolating stimuli get created, and how one can compute cone responses using cone sensitivity response vectors.